In this tutorial I'm going to explain what a Cubemap Skybox is, and I'm also going to demonstrate how to produce a Skybox by using 3 different rendering methods. The code for this tutorial is continued on from tutorial 9, keyboard, mouse and joystick input, but you can also incorporate the relevant parts of the code into tutorial 5, model loading part 1. Let's begin by considering that a Skybox consists of 6 individual photographic square images that form a cube. Each of those photos represents a 90-degree field of view of the scene. When viewing a Skybox within a game or application, the view is only truly correct if the camera position is at the cube centre, although if I move away from the centre just a little bit as I'm doing now, it still does look reasonable, but then when I return to the centre, the difference is actually quite noticeable. In reality, if a camera position changes, then the amount that can be seen of each side of any given object should also change, but it can't because the only visual data available is from a single viewpoint. As I'm now rotating the camera in Blender, notice that you don't see any more or less of each of the 3 spheres, unlike when I change the camera's position. Having said all that, you might still be wondering why it doesn't look distorted at the corners. How can it be that 6 flat photos somehow appear as being the spherical scene? One great way to help visualise the situation is to also use a sphere as well as a cube, and then by adding a simple mesh such as a cylinder to represent the line of sight, we can then clearly see that the line of sight intersects the same pixels as it passes through both the sphere and the cube. Also notice that as I toggle viewing each of the spheres on and off, then when looking from the camera's point of view, the missing top face of the cube becomes partially filled with the scene image. When only the smaller, chunkier sphere is visible, you can even see the imperfections of how having fewer faces results in noticeable pixel misalignment. The reason that the 6 flat images correspond to the one spherical image is because camera lenses are also curved, and so when you're looking at a flat photo, you're actually seeing a spherical view. Also notice that as I scale the cube or the sphere, then as long as the camera is positioned at the centre, the line of sight still intersects the same image pixels, which is because Skyboxes are optically equivalent to real-life 360-degree views of the world, without any need for programming or mathematical magic. Although the Skybox itself consists of 6 90-degree field of view images, which corresponds to setting the field of view value to 45 within a game, the projection matrix field of view that is used to view the Skybox does not also have to be set to 45 degrees for the scene to look correct with respect to the field of view related distortion that does occur. Instead, as I'm now adjusting the field of view, the internal angles of the view frustum's 4 direction vectors either increase or decrease as they intersect across one or more cube faces to capture the scene, which respectively also has the effect of minifying or magnifying the resulting view, and also creating distortion towards the sides, the more the field of view is increased. Assuming that the Cubemap images are not distorted, then the amount of field of view related distortion that occurs when rendering a Cubemap as viewed from the cube centre is the same amount as for 3D spatially rendered objects. Therefore, you can choose any field of view you like for the projection matrix that is used to view the Skybox, and the resulting image will look the same as if rendered from a real 3D scene. The image format that is used to store 360-degree views is called Equirectangular. Notice how the top and bottom regions of the image appear very squashed, which is due to having converted the entire 360-degree spherical view to a single rectangular view. However, an equirectangular image can be converted back to being spherical, or indeed converted to 6 Cubemap images, both without any distortion whatsoever, although the conversion process does result in a varying image resolution. There's a website linked to in the description called Polyhaven, which has hundreds of HDRI images that you can download and use for free. Make sure you select the 16K version if you're developing games for Quad HD monitors, and especially for 4K monitors. Otherwise the 8K version, which converts to 6 square 2048 pixel images, should be fine. Here's a quick comparison of 8K versus 16K with the field of view reduced to 20 for demonstration purposes, as displayed on my HP Quad HD monitor. Notice that the trellis looks sharper in the 4096 pixel image on the right compared to the 2048 pixel image on the left. For the file format, you can select either HDR or EXR, but HDR is the more widely supported of the two, and therefore probably your best option. To convert equirectangular images to their corresponding 6 Cubemap images, there are several free equirectangular image to Cubemap converters available, which I've also put links to in the description. Of those 3, I'm going to demonstrate how to use the Panorama to Cubemap online converter, but first we need to convert the image to a compatible type. such as JPEG or PNG. GIMP is a graphics editor that you can download for free and use to save HDRIs as different image types, or if you have Photoshop you can use that instead, which is what I'm using. You can also adjust the exposure of the HDRI to reveal more detail. If you now select your Equirectangular JPEG or PNG file, the 690° field of view Cubemap images will be generated automatically, and then to save them to your PC you just need to click on them one at a time. To create a Skybox in Blender that you want to export as an object and material file to load into your game or application, you need to delete the default UV map, open the UV editor window, and then unwrap each face and apply the corresponding image textures as already converted from your Equirectangular image. By looking to see if the edges of the image line up with adjacent images, you can then rotate and or reverse the texture coordinates if required. However, if you want to look around the 360° view of the Skybox within Blender, then you need to follow the same procedure but turn off the shading by selecting emission for the surface option before selecting each image, although that will also stop the image names from exporting to the material file, but just for viewing in Blender it works perfectly fine. Also note that when we get to rendering a Skybox in our application, which we'll look at in just a moment, you can also affect how the image appears by reversing the texture coordinates in the vertex shader. Flipping the x-axis in the vertex shader works perfectly, which can be simulated in Blender like this. We can also reverse the z-axis, but that also causes the initial view direction to be looking backwards. Reversing the y-axis also works, but then everything is initially upside down. So by flipping any texture coordinate axis, you're effectively turning the cube inside out. Alternatively, you can also flip the Equirectangular image in GIMP or Photoshop. To move the camera to the scene's centre, first make sure the cursor and the cube are both positioned at centre, then select the camera, choose selection to cursor, and then finally set the camera's rotation values as desired. Another much quicker way of producing a Skybox in Blender is to use Blender's environment texture option, which automatically applies the Equirectangular image format to the entire cube. Or you can simply select the standard image texture option and apply the Equirectangular image to a sphere instead of a cube, which can then also be exported for importing into your game just like a normal model, without needing to involve cubes at all. At the beginning of this tutorial I said I was going to demonstrate how to produce a Skybox by using 3 different rendering methods. The first method is to simply render a cube that's been imported from Blender, created just like the first cube which I drew earlier. All you need to do then is import the cube from the exported Blender file into your game or application, as explained in the Model Loading Part 1 tutorial, and then also set the GLM view matrix position values to 0, 0, 0, which is of course the centre of the scene. Alternatively, you can update the position of the Skybox to be the same as the position of the camera, or vice versa, although there are also other methods which we'll look at shortly. I've also added 3 new features simply to help demonstrate cube maps for this tutorial, as follows. There's a uniform used to control adding the vertex normal values to the Skybox vertex position values, which causes the sides of the cube to move closer together or further apart. There's also a uniform used to control the size of the cube, and the field of view is adjusted by recalculating the projection matrix, which is controlled by the joystick. And there's also this dirty quick fix in the fragment shader, which simply overrides all the previous fragment colour calculations by setting the texture's colour to be used directly, thereby disregarding all the lighting effects. Disabling the depth test causes all the other models to be rendered over the top of the cube, or indeed spherical world, even if they're positioned behind it in object space, which also means the size of the cube doesn't matter. For example, when the sphere is positioned at the side of the main scene, notice how you can always see the scene even when the sphere is positioned in front of it in object space, compared to how it looks now, which is with depth testing enabled. Also, when depth testing is disabled, if I then translate the camera position to the centre of the sphere, notice how the scene models are still perfectly visible. The second method is to use OpenGL's built-in Cubemap sampler functionality, for which I'm using manually entered vertex data instead of importing a cube from Blender. We let OpenGL handle calculating the texture coordinates of each vertex by providing OpenGL with a 3D direction vector that points from the cube's centre to the vertex position that is being rendered, and so a 3D direction vector from the cube's centre at position 0, 0, 0 to the vertex position is simply equal to the APOS value. The term major axis simply refers to the cube's 6 perpendicular directions from its centre, or in other words, simply the distance of its width or height divided by 2. I've put a link in the description to this Cubemaps article by NVIDIA. For example, here's the calculation for a direction vector that intersects the far face 1/4 of the way across from the left for a cube size of 10 units. Loading each of the 6 images is accomplished by passing a vector which contains the file path of each image to the load Cubemap textures function, which then loops through loading all of the images. Setting up the vertex array object is done the same as in the previous tutorials. Loading textures is also very similar, apart from we're now binding a Cubemap texture instead of a 2D texture. The first argument for defining the texture image now corresponds to a cube face, and there's also an additional texture parameter which is equivalent to the z-axis in object space, which corresponds to the third component of the 3D direction vector. Note that if we use GL linear instead of GL clamp to edge, the seams at the cube's corners will be visible, or we can leave it set to GL linear and enable GL texture Cubemap seamless instead. Also notice that OpenGL supports the use of mipmaps with Cubemaps. The last important aspect to consider for this second method is the view projection matrix, for which there are 3 options. We can use the player's view projection matrix as usual, but then also continuously translate the position of the skybox to the camera position. We can simply avoid having to translate the skybox position by disregarding the positional values of the player's view matrix, but still use the player's projection matrix. Or we can create a dedicated projection matrix especially for viewing the skybox, which has the advantage of being able to set a different field of view. For example, this is what it looks like if we set 70 for the skybox but only 35 for the main scene. Notice how there's field of view distortion towards the edges of the skybox, but virtually zero distortion of the main scene. Let's now have another very quick look at the vertex shader and the fragment shader, which are both very simple. Within the vertex shader, you simply need to pass the input attribute position values to the fragment shader, which are then used as the Cubemap sampler's 3D direction vector, and of course multiply those position values by the view projection matrix. All you need to do within the fragment shader is to call the texture function, passing in the cube sampler and the 3D direction vector. The third method is to render a full screen quad instead of a cube. The code that I'm using was originally posted on Stack Overflow about 7 years ago, so thank you to Derhas for posting it, and I've also included a link in the description to the post. To use the Cubemap Skybox class to render the full screen quad instead of the cube, it requires commenting this section, which will then create an empty vertex array object, and also calling GL draw arrays with GL triangle strip instead of GL triangles, and for depth testing to be disabled. This method involves using array projection type technique, whereby 4 attributeless XY position values and also Z position values are used to represent the 8 corners of the normalized device coordinates NDC cube. 1 GL vertex ID per shader iteration is converted by the bitwise operators to an NDC cube XY value. That XY value is then given Z values of 1 and -1, thereby representing 2 of the 8 NDC corners. Each of those 2 position values is then multiplied by the inverse of the player view matrix, which converts them to clip space. Perspective division transforms those values from clip space to become a 3D direction vector in object space that consists of one of the 4 points of the far plane and the corresponding point of the near plane. Subtracting the near plane point from the far plane point gives us a direction vector within object space for that particular leg of the view frustum. One last thing to mention is that the positional values of the view matrix make no difference to the result, and so they can either be left in or disregarded. When running the program, we can reveal it's actually a quad being rendered by zooming out, continuing to look around the scene, and then also rotating the quad. Hopefully you'll have found some of these demos amusing, and if so, please don't forget to subscribe. Cheers.